Okay, so our learning goal today is to take what we learned with the vector and parametric equations of a plane and to determine the scalar equation of a plane. And as you recall, when we did the lines in 3D, I had said that we can't have a scalar equation of a line in 3D because a 3D scalar equation will always represent a plane. And you'll be able to recognize it because there's a z component. And if there's no z component, then it should be stated somewhere. All right, so the scalar or Cartesian equation is ax plus by plus cz plus d. So this cz plus d, that's kind of like the new part. It looks a lot like the standard form of the equation of a line. However, we have a new variable z, and then we have a constant d instead of a constant c. The way that we're going to generate this equation is we're going to work with the principle of a normal. So a normal is a line that's perpendicular to a line or a plane. So that's this purple vector that is, or actually I'm going to turn it blue. So that's this vector right here. And it has the components A, B, and C. So as long as I know what that normal is, and I have a point on my actual plane, I can figure out the scalar equation. So what we're going to do is sort of kind of prove where this equation is coming from, and then we're going to figure out some equations. So put it into practice. Okay, so here, again, I have my plane. So I have point P, so I just arbitrarily chose a point. And then I have another point P naught right here. So these create a vector. This vector right here lies in the plane. The blue vector that I've drawn, that's a normal. So again, it's a vector that's perpendicular to the plane. Whether I draw my normal there, or I draw it over here, or I draw it down here, they're all the same thing. So what I'm doing is I'm taking it and trying to show that it's perpendicular to this direction vector. To show that two vectors are perpendicular, the easiest way to do it is to use the dot product. So that's what's going on with all this stuff. But before I get into the dot product, I have to actually generate the vector that I have drawn in purple. So point P has the coordinates x, y, z. P naught, I'm saying, has the coordinates x naught, y naught, z naught. So this expression right here, this is just the vector that I'm generating. And I have to leave the variables there because I don't have numbers. So then I want to show that these things are perpendicular, or use the idea that they're perpendicular to figure out what's going on. So that's what's going on right here. So this is the dot product. What's happening in the next step is I'm actually doing the dot product. I'm taking the A and I'm putting it with x minus x naught, because that's the x component. We're going to take the B and we're putting it with the y components. And we're going to take the C and put it with the z components. So that's what's happening in this line right here. So I've expanded it. Now I can't really simplify it that much right now, but what I am doing is I'm going to put the AX, BY, and CZ. So I've pulled that out in front. You can see that it's starting to look a lot like that standard form for the equation of the plane, or the scalar form. So I have AX plus BY plus CZ plus I have AX naught minus BY naught minus CZ naught equals 0. This expression right here, that represents the D. So we know what these numbers are, so we can always figure out what this D value is. So based on that, the normal that has the value A, B, and C, those are the coefficients that go with the X, Y, and the Z. So our goal is going to be, how am I going to be able to figure out what that normal is? So let's look at some examples. So here's our first set of questions. So consider the plane that has normal vector n 3, negative 2, 5, and contains the point P naught 1, 2, and negative 3. So to get the scalar equation of the plane, I am going to sub in my normal for the A minus 2y plus 5z plus d. So just having the normal, I already know what A, B, and C are. I want to know what D is, so that's where the point comes in. So now I'm going to substitute in that point. So I have 3 multiplied by 1 minus 2 multiplied by 2 plus 5 multiplied by negative 3 plus D equals 0. So when I expand that out, I have 3 minus 4 minus 15. So that's giving me minus 16 plus D equals 0. So D equals 16. So that means the scalar equation of this plane is 3x minus 2y plus 5z plus d. Whoops, I actually know what d is, so I'm going to replace the d, plus 16 equals 0. Done. So as long as we have that normal, fairly straightforward question. Okay, now in part B. So it says, determine if vector A is parallel to the plane. All right, so if it's parallel, so I have my plane, I know my normal, so I'm trying to see, is the vector parallel? So if it's parallel, it has to make a 90-degree angle with the normal. So we are going to see if A dot n is equal to 0, because perpendicular lines have a value of 0 for their dot product. So we will have 4 multiplied by 3 plus 1 multiplied by -2 plus -2 multiplied by 5 equals 0. So I have 12 minus 2, that's 10, minus 10, so we get 0 equals 0. So is it parallel? The answer is yes, it is. Okay, now the next question for C. Determine if vector B is a normal to the plane. So is B a multiple of our normal? So if I look at it, 5 times the normal will give me B. So therefore, yes, it is, because they're scalar multiples of each other. So it's just going to be a longer version of the exact same normal. Now finally, in question D, determine another vector that is normal to the plane. So if my normal is 3, -2, 5, any multiple of that. So one of the easiest one would be -3, +2, and -5. So it's just going in the opposite direction. So it doesn't say that it has to be pointing out of the page. It could be pointing into the page as well. Okay, so in this example, find the scalar equation of a plane containing the points A, B, and C. Okay, so these are points, they're not vectors. So I have to, first of all, to get the scalar, I need the normal. So normal is a line that's perpendicular to two direction vectors at the same time. Gee, I wonder what that's the definition of, the cross product. So I'm going to start off, I'm going to generate vector A, B. So when I get AB, I'm going to have 7, 7, 4. I'm going to use BC this time. So BC, and again, you could use any two direction vectors here. So I have 1, 10, and -1. So my normal that I'm going to be looking for is equal to the cross product of AB and BC. So when I find my cross product, so I'm going through my process, I am going to end up with 33, 11, and -77. So that's the normal. Now you could leave it like this, but if you notice, they're all divisible by 11. So it's much easier to work with 3, 1, and -7 than it is 33, 11, and -77. So you can always reduce. It's not wrong if you don't. It just simplifies the numbers a little bit. So this is the standard form, or the scalar equation. So I know A is 3, I know B is 1, and I know C is 7. So now I need to find D. In order to find D, you can pick any one of those 3 points. So I am going to sub in point C. So 3 multiplied by 5 minus 4 minus 7 multiplied by 1 plus D equals 0. So 15 subtract 4 is 9. No, 15 subtract 4 is 11. minus 7 is 4. So we have 4 plus d equals 0. So d equals negative 4. So that tells us that our equation, it's not a, we know what a is. So our equation is 3x plus y minus 7z minus 4 equals 0. So some of you were wondering what other application can we use the cross product for? Well, we can figure out what the normal is. Okay, I believe I have one more set of examples. Okay, so determine the scalar equation of each plane. Okay, so here it tells us it's parallel to the xz plane. So let's just do a little sketch here. Okay, so we know x is here, y is here, and z is up here. So that xz plane is right here. So if I picture my normal, the normal is the what? The y-axis. So what can we use to represent the y-axis? That's right, the unit vector. So my normal would be 0, 1, 0, or we could call it the j unit vector. So that's my normal. So I have 0x plus y plus 0z plus d equals 0. So right now I've got that simplified down to y plus d equals 0. So when I'm substituting in my point, I only need the 8. So 8 plus d equals 0, which means d is negative 8. So the equation of this plane is y minus 8 equals 0. Okay, so for this one, it's saying it's containing the line. So it's containing the line and it's perpendicular to this line. Okay, so I have a plane. I have this line on it. And then it's telling me the other line is perpendicular to the plane. So if it's perpendicular to the plane, this is your normal. So we have 2x plus 3y minus z plus d equals 0. I have to sub in a point, so that's the point that's on the line. So I have 2 multiplied by 1 plus 3 multiplied by 2 minus 4 plus d equals 0. So I have 2 plus 6 is 8 minus 4. So 4 plus d equals 0. D equals negative 4. So this equation is 2x plus 3y minus z minus 4 equals 0. So a lot of these questions, it's very much being able to take the information that's being given to you and figure out how you can generate the normal.